2014 Waves Level 2, Question 2. And we're at the beach. Moana is swimming under the water. She can see a fish, and she can also see the image of the fish caused by light reflecting at the water-air interface. So that's some light that's bouncing up here and reflecting down there. So she can see it directly and see the reflection. A, state the full name of the process by which Moana can see the image of the fish reflecting at the water-air interface. Draw one ray on the above diagram to show this process. So this is a bit of a gimme question really. This is the full name of the process. It's not just reflection, it's total internal reflection. Okay, and one ray, you'd be safe to draw the normal. Here's your ray, arrow showing the direction of the ray, should always show you arrows, and Moana's eye. You can draw the arrow in any position. Also a good idea to show theta I, theta r, and theta I equals theta r. Angle of incidence equals angle of reflection. So there we go. Question B. Critical angle at the water-air interface is 47 degrees, so that's theta c. The refractive index of air is 1.0. Calculate the refractive index of water. Sketching a diagram again. We've got our normal, we've got our light ray that's going in at the critical angle. C, that's our fish down there. So light coming from the fish bouncing there. Critical angle is defined as the angle beyond which total internal reflection occurs. So we can take this as the reflected ray being at 90 degrees. So this is going to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. And theta c can be N1, and that means theta 1 I should say. And N1 therefore is going to be the refractive index of the water, because the water goes with the angle in here. Different colour, green. N2 is going to be the refractive index of air, and theta 2 is going to be our 90 degrees. And since that's 1.0, 90 degrees, you end up with a 1.0 on the right hand side. So 1.0 equals N1 sine theta 1, which is sine 47 degrees. I'm getting a bit mixed with my colours now, but our final thing we're going to get is N1 equals 1.0 divided by sine 47 degrees. Okay, and you can calculate that out. Go through again if you're not sure how I've come to that answer. C, a beam of red light passes, let me just move this so that we're not distracted by the clutter. Beam of red light passes from the air into the water. Calculate the wavelength. Let's draw this. Red light, I'll just say it's red even though it's blue, passes from the air into the water. Okay, we're just assuming it's going straight through the boundary at the moment, not considering any refraction. We can modify a diagram later if we need to. Calculate the wavelength and the frequency of the light beam as it travels through the water. So wavelength water and the frequency water. We've got V equals F lambda to link both the frequency and the wavelength. V is going to be the speed of light. So we can write that as C. The speed of light is given to us there. So that's going to fit into there. And the wavelength of light in red light in air, 6.5 times 10 to the minus 7. Okay, that happens to be 650 nanometers. Okay, so we've got a formula here. If you remember, the refractive index in one medium divided by the refractive index in another is equal to the wavelength in that one medium divided by the wavelength in the other medium. Now, just got to mentally check, is this right? Let's just check it by doing it this way. If this was air and water, then that would mean this is the left-hand side would be approximately equal to, refractive index is the air has got to be lower than water, so it'll be less than 1. So the right hand side has to be less than 1. That means we need the larger number on the bottom. The wavelength in water is actually going to be less. Okay, the wavelength in water is going to be less because the speed will slow down in the water. So we've got this round the wrong way. We need to have 2 and 1. There we go, good check. Very good check to do, eh? So going over that again, wavelength 2 over wavelength 1. Use the formulas. I mean, if you didn't know, you could just find the formulas and plug it into it. But use that, plug the formulas in, rearrange for the other one. So once you've got the wavelength, now this is a little bit tricky because we don't have the speed of light in the water, do we? So what would we do for that? The same thing could apply. Let's go back to red because we need another colour. Is that this also equals the speed in medium 2 divided by the speed in medium 1. So medium 2 is going to be slower. It's going to go, the speed of light in water is slower than in air. So yeah, it's going to be around that way. That's good. So we can use this to find the speed of light in the water. Let's go to yet another colour. I'm going to use grey. We've got refractive index of air, which is 1.0. We worked out the refractive index from water above, which is good, though we don't actually have to use it now that we've got the 2 outside bits. We've got the speed of light in this is air. We've got the speed of light in air. We don't know the speed of light in water. We've got the wavelength in, what's that one down the bottom, in air, and the wavelength in water. Well, if we use the information from above, we can calculate that, and we can also calculate that. It's just rearranging the equations. If you're not sure, ask me, otherwise come back to it. Also check in with the exam solutions. I'm trying to keep these video lengths down, as I keep on saying. Okay, tricky. Carrying on, D. I think this is the last one. Yep, D. Moana's in her garden, which is outside her room. There's a radio playing in her room. So I guess this is the door, this is the room. Radio playing in a room and the door of the room is open. So comparing the wavelengths of light and sound waves, discuss why Moana can hear but not see the radio. Okay, so presumably there's no way for visible light to somehow bend around and come through so that Moana can see it. But she can hear the sound waves somehow. Okay, we would assume that it acts like a point source. There might be sound radiating out there. To get through that gap, the sound has to kind of somehow travel in that direction. We're going to get sound waves going off in that direction, spreading out in the circular wavefronts, probably bouncing off walls and coming back, and that way you get some of it passing around. So that's one way, okay. That's physically what's going to happen. Now, they're not actually interested in that sort of detail, but that helps you to think about it perhaps. What they're interested in is the idea of diffraction. And if you can see the wavelengths of light, which is very small, and the wavelengths of sound waves, which is larger compared to that, you're going to get more diffraction with the larger, with a larger wavelength. Okay, when the wavelength's so small, you're not going to get any significant diffraction, and that'll help you to see it. But to be perfectly honest, I think this is more, in reality, to do with the vibration of the sound through the walls and the floor and everything, and the bouncing around of the sound waves off walls and other surfaces. Light waves will still do that too, but any colour of light from the radio that's been given off is going to be absorbed by the walls unless the walls are exactly the same colour as the radio. I'm going to confuse you if I carry on with that. But the idea of diffraction, larger wavelengths will diffract more. And there you go, that's question 2.